Thank you. So yes, Caulk is, I'm very excited about giving this talk today because Caulk is like 4 months old now. And this talk is going to be quite different from the one in the ZK Static Lab because things have happened in 4 months. And that's super exciting. So this is work we have done with Vitalik, Dimitri, who is also here, Mary, Mark and Anka, and earlier this year, well, I was intern at the Ethereum Foundation. So let's start with a bit of motivation. Caulk has like 2 key applications, lookup tables and membership proofs. And I'm going to dive a bit deeper in both of them. So for membership proofs, like we can think of applications such as anonymous credentials or the Zcash protocol. And the idea is like, I want to prove that I belong to some like authorized set of people. And this set of people is public, right? And we are all represented with our public keys. And in order to prove myself into this group without leaking information about my identity, the first thing I would do is like isolate my public key. But with this yellow zero knowledge key, so the idea is that I can prove that whatever is here belongs to the set. And then I can prove knowledge of the corresponding secret key, and so I can prove that I belong to this set without really leaking information. So for this to happen, it's important that I don't leak the value that I'm isolating, but I don't leak either the position. Both things will lead to my identity. For membership proofs, Caulk is like especially nice because previous approaches, like most of the applications, use this like market tree approach that we are going to see later. And like in numbers, in the implementation we bet them by like 100 times. So we are 100 times faster than what is being used today. For lookup tables, what we have is instead of a hidden element, we have a hidden set. And once again, we want to prove that all the elements that are in this hidden set do belong to some public set. Maybe they are repeated, we don't want to leak positions, we don't want to leak values. And lookup tables are exciting because we can think of them as generalization of range proofs. So in range proofs, we have, again, one element that we have like in zero knowledge, and we want to prove that it belongs to some range. A way of doing this is like, once again, linking it to some public set that, for instance, in this case, could contain all the values in the range. And when we use lookup tables as like range proofs, we can really speed up like snark provers. And also, when we use them, like for instance, to replace like hashes, to prove that something is the output of a hash, it makes a big difference in, for instance, in the circuits that we need to design for the zero knowledge Ethereum virtual machine. And it makes a difference between a circuit that we can prove and one that it's like basically not practical. So all these problems, range proofs, lookup tables, membership proofs, have been tackled before by other works. And basically, I will say we can like divide them in 4 groups. We have discrete log solutions. They have trusted setup, transparent setup, so that's super cool. But usually we need both prover and verifier to be linear in the size of the big set, in the public set. So we are like wasting time here, right? Then we have like RSA accumulators solutions, which seem, like, can you see it properly? Okay, sorry. So RSA accumulator solutions seem like perfect. We have a constant prover, a prover that does not depend on the size of the big table, but we also have a constant verifier and a constant proof size. But we have trusted parameters. And if you are like familiarized with Caulk, probably you will tell me you also have trusted parameters, but they are not quite the same kind of trusted parameters. We have like ceremonies, multi-party computation in order to perform our trusted parameters, but with RSA accumulators in order to instantiate these groups, things are way more complicated and impractical nowadays. Then we have the Merkle tree solutions, which are the ones that are all around, ZK8 protocol, for instance. And it's nice because, again, we have a transparent setup, but then we need to put a zero-knowledge snark on top of a Merkle tree. And Merkle trees have a lot of hashes. So this snark has a prover that is linear in the size of the circuit as all the snarks, but in the size of a very big circuit. So again, this is not ideal. And for pairing-based solutions, which we have a bunch, we have consent proof and consent verifier, but usually the prover is linear. I mean, before Caulk. So Caulk lies in this setting. We work in the pairing-based setting. We have a logarithmic prover in the size of the big table, so that's a huge save. And we have also consent proof, like most of pairing-based constructions. And our verifier is still like dominated by a constant number of pairings and has to perform field operations in the field. So let's see, how do we construct lookup tables with a fast prover? So we don't want our prover to be linear in the size of the big set. That's what we need, right? To get rid of the elements that we don't use. And I will give you the recipe for this. What does Caulk actually do? We start with this big public set of size n. And first thing we are going to do is create a subtable. So if our hidden set is only taking some elements of this table, we don't want to work with all of it. So the first step to become non-linear is just get rid of the size n, the big table. And of course, this subtable will need to be hidden as well, because we don't want to leak information about the positions or the values that we are isolating. Then we have to prove, of course, this subtable is well-formed. It's indeed a subtable of the big set. And then we can link it to our hidden set. That I would say the hidden set has size m. And I hope now it's a bit more intuitive that we can actually do this in time that does not linearly on the size of the big table. It should be faster, right? We have something way smaller, which is the subtable of size k. And we have our hidden set that has also size m, smaller than the big set. And this recipe works. It did work for us. So I have some benchmark here. This is the representation of comparison with previous work in membership proofs. Our prover has size log n, so it's logarithmic on the size of the big table. Caulk is the orange line that you can see below. So in the y-axis, we have prover time in a logarithmic scale. So this means that we are order of magnitudes better than the closed resolution. And in the x-axis, we have the size of the big set. So we go from sets of size 2 to the 6 to 2 to the 22. We can say, we can claim that Caulk performs better than other solutions for basically any practical set. The red line, the second one, the pointer is not really working, but the red line corresponds to RSA accumulators. We said they have constant prover, so it doesn't really matter how big is the set we are working with. And then with the green line on top, we have Merkle trees with Poseidon hashes. So even with Poseidon hashes, we are 100 times faster. And the pink line at the very top is Merkle trees that are constructed with SHA hashes. So for membership proofs, we did pretty well. And then for lookup tables, the thing changes a bit. So at the very top, we have Merkle trees with Poseidon hashes and a snark on top. They are obsolete, hopefully, compared to the other ones. And in this case, we have, again, prover work in a logarithmic scale in the y-axis. And in the x, we have the size of our hidden set. So for lookup tables, we are not isolating one element, but a bunch of them. So we try numbers from 10 to 50, small sets. And the line, the color of the line is what is represented the size of the big set. So the blue line is two open sets of size 2 to the 8. So if my public set has size 2 to the 8, we go from 10 elements to 50. Caulk performs quite well. In the orange line is when we start with public sets of size 2 to the 20. Caulk still performs nicely. And then the red one is RSA accumulators, only one line, because again, in RSA accumulators, we don't really care about the size of this public set. The thing is that we only computed up to 2 to the 20, because that's everything my laptop could handle. But if I will say that for sets of size 2 to the 23, 2 to the 25 already, Caulk performs worse than RSA accumulators. And also, like you see, our prover has size m squared plus m times log n. So it depends logarithmically on the size of the big table, but quadratically on the size of the hidden set. And this will probably have, whoa, that's this, okay. Okay?
You want to change mic? Yeah, you're saying it's like change mic.
Okay.
So, just give that like 10 seconds. We'll swap.
No worries. Okay.
Swap this one in. There you go.
All right. Is it on?
Take 2. They'll turn it on.
Okay, perfect. So also this m square like element will play a role for bigger sets, hidden sets. So in the axis we may get also worse. If you see in the orange and the blue lines, like the slope is growing slowly, but this is growing. So this is what we care about here. We like all the improvements we are going to talk about are like on getting rid of this m squared and logarithmic log of n thingy. So how do we actually follow this recipe in Caulk? Let's talk about like concrete stuff. To create a subtable, first we use like KCG commitments to polynomials that encode the vectors with Lagrange interpolation. So for the big table, we need a set of Lagrange polynomials of size of degree n-1 that will correspond to a set of root of unity of size n. But for the subtable, we are creating a subtable because we want to work with smaller things. So committing to the subtable with the same set of Lagrange polynomials would be like nonsense. So what we do, it's like commit to it with another set of Lagrange polynomials that correspond not to the entire set of root of unity of size n, but only to those that represent the values we care about, that represent the positions we care about. So this other polynomial that has that is also interpolated using root of unity will have only degree k-1. And this is an idea we took from this very nice work from Tomescu et al. What we also took from there is the proof of all formation. So we can create the subtable, we can commit to it, and communicate it with a small polynomial, and then we can prove that it is well formed with the prover only will take like time k, not m, sorry, that's a typo, given that we have a pre-processing that is linear in the size of the big table. So we can get rid of the big table somewhat, but we pay a price, which is in the pre-processing. And this is, I would say, fair enough. Then our prover is k, just like cheap, small. The thing is that in our setting, we also want zero knowledge. This is not something that was considering the work of Tomescu et al. And to achieve zero knowledge, we need to prove well formation of some like vanishing polynomial. I'm not going into the details. We have a very nice protocol for this. It's like 7 pages, 2 columns, and it takes time m times log n, which is good. That is the m times log n that we have in the benchmark. And then, I think it was 2 months after we released Caulk, we got this email from Jim Posen and Katie's, and they were like, hey, why there is this other way of doing things. Have you considered it? No, we didn't, and it was way better. They reduced this to n, which implies that now the lookup table, as the title says, is independent of the big table. Modulus the preprocessing, but once we have the preprocessing, that's it. We don't care anymore about this big n. So this was great. We only have now m squared plus m. And as I said before, once we have the well formation of the subtable, we can get rid of the big one. We don't care about it anymore. And now what we have to do is just link this subtable with our hidden set. Our hidden set will also be committed with a KCG commitment as an encoding of the vector. And if you see, we are working with a different set of polynomials here, a different set of Lagrange polynomials. Why? Because the first one we are using, that is public, has size n. We don't want anything to have size n here. Then the second one, the taus, those are secret. Those are Lagrange polynomials that will leak information about the positions that we are opening. So we need another one. We need a public set of Lagrange polynomials we can work on later. This will give a bound. Yeah, it's what we call m. So assuming that m is way smaller than n. And now our problem is to link these two guys, the subtable with the hidden set. And in Caulk, this is what takes time m squared. And this is what we want to improve. This is all I'm going to talk about now. So we have two polynomials. We have two polynomials that are called vectors that we want to link. What we want to prove is that everything that is in your right side, so all these a's, are actually the same as one of the b's in the left. So everything that is there has been taken from here. And this is nothing but a lookup table itself, right? This is exactly what lookup tables do. With the difference that we have this, the hidden set keeps being hidden, as in previously, but now we have that the table itself is hidden. It's not only hidden, but it's also in an unknown basis. A basis that the prover makes itself and has to keep secret. So, I mean, it's not the same, but I think we already have a starting point here. We just need to construct lookup tables where the prover can be linear on the size of the table, because now our table is not n, it's just k, it's way smaller. So our prover can be linear on that, and we have lookup tables for a linear prover in the pairing-based setting. So the idea is that what we have to do now is just adapt these ideas so the table can be hidden. So the first approach we are working on with Mary, Dimitri, and Ariel is to use lookup. So Ariel says, okay, this basis is unknown and it's bothering me, so let's avoid it. We don't commit with Lagrange polynomials anymore, but the commitment to the vector, to the big table, is going to be a vanishing polynomial. A polynomial that vanishes at the values of the vector. So no more root of unity or anything like that here. This is work in progress, but let's say good progress. This approach gets very good constants, and apparently pretty sure we can get rid of the pairings. So this can be instantiated with other kind of polynomial commitments. The bad thing is that we need quadratic precomputation. So instead of n, it would be n squared. And the commitment is not homomorphic anymore, but for some settings where we don't want to really update it, should be okay. The other approach is to use snark techniques. And when I say snarks, I say matrix and vectors. So if you're familiar with Marlin, or if you are familiar with R1CS, all we do in snarks is try to prove like linear relations like this. That some matrix multiplies some vector equals some other vector. And this is the relation that holds for Ci and Phi. In snarks, like usually what we have here as C and I, are like the witness, are part of the witness, so we keep them secret. But now the challenge is to keep secret as well the matrix. Because the matrix is what will select which elements of C are going to be in A. This approach has homomorphic and updatable commitments, so that's nice. But of course, it's a snark technique, so it has like the bad snarks concepts. So, what to expect? For pairing-based solutions, we already have like Lookup and Halo. Those are linear in the size of the big table. So they come out like to be very good for small tables where we look up at many things. So where the hidden set is big, but the table is small. And for Caulk, right now it's quite the opposite, right? We are quadratic in the size of the small table. So if the public set is big and we are looking at like small pieces of it, this works well. The question is like if we can get the best of both worlds, which I mean just linear in the size of the hidden set. I say yes, sure, but I say it like small because we have to do the proofs yet, but that's where we are right now. Thank you. Perfect. Sure.
We're going to do about 5 minutes of questions here. I'm going to come around with a mic, so please raise your hands if you have a question for Arantxa.
Hey, you mentioned that your setup is better or different than the types of like NPCs that have been proposed for RSA stuff. Can you unpack a little bit like why that is?
Yes. So I don't know how familiar you are with KCG polynomial commitments, but the idea is that the setup is trusted, but it's something that you can compute using multi-party computation, these famous like ceremonies. And also it's universal. That means that you can construct a very big like setup and reuse it for many different like kind of protocols. And then the thing with RSA accumulators, which is not exactly what I do, so I hope I'm not going to make any mistakes here, but theoretically we could do the setup with multi-party computation, but in practice, no, like nobody has done it. So you really need one trusted party for RSA accumulators, while for pairing-based like vector commitments or even snarks, these updatable and universal snarks, you have like a better approach, which is multi-party computation plus do it very well once and then you can reuse.
Yeah, we don't have mics, so just speak up your question loud.
Yeah, hi. Thank you for the talk. Just one question about the pre-processing. Can you say a bit more about that specifically? What is the size of the pre-processing that the prover has to keep?
So, do I have the slides? No, I missed them. Okay. No, it's okay. We will have to go back quite a bit. But the thing is that in order, here, so in this work, the thing is that when you like prove well formation of the subtable, you have to relate it with the big one, and that should take size n. So this is an equation where you have to compute polynomials of size n. In this work, what they say is, okay, you can pre-compute, I would say, this proof of like well formation of subtables for subtables of one element, but for all of them. So basically, you open the big table at every one of its elements, and that takes time n log n, sorry. But the size is n, the computation of this setup is n times log n. And then, once you have that from this set of n proofs, you can compute the proofs for every subtable on time that depends only on the size of the subtable. So in this case, I will have all the individual proofs for all the A's that belong to the subtable, and then I just aggregate them basically with some constants, and I got the proof of well formation. Was it clear? Perfect.
Any more questions? Oh, Henry in the back. Can you just speak it up? Yeah, we don't have the mic.
Yeah, sure. What I'm wondering is there a way to sort of bridge these techniques with something that would let you do like efficient updates to what the sets are? Right, like, so, because the point of sort of the previous talk is that like it's not actually just the proving time, but also like how do you actually know what the set is if that's evolving over time? And I'm wondering is there some way that you can do like incremental updates?
Yes. So as Caulk is right now, updating the set is possible. But the problem is that you have this pre-processing, so you have already like computed the opening proof for every element. And with KCG commitments, if you change one value, all the proofs change. So this is not ideal. Still, there is a way of computing these KCG proofs like in a tree fashion, let's say, like not a Merkle tree, but as a tree. And once you have that, you can like update chunks of the set and like get rid of this like recomputing everything. So yeah, Caulk for now, I will say you only use it if you have like a table that will stay like as it is. And then you can do some other tricks, and actually we have a work after this on like maintainable vector commitments that you can trivially apply Caulk to.
And then one last one under the wire is, can you also do proofs of non-membership?
No. Actually, there was a discussion on Twitter about this. And Jim, the same guy from Caulk Plus, he kind of had an idea, but to be honest, I didn't check it. But apparently, like, I mean, I would trust him after the improvement he found. But yeah, I will say there is something there, but I cannot assure it works.
All right, please give Arantxa a hand.